Hello and welcome to EC260 Lab. Today we're going to cover Lab 5 induction motors. Let's go over the lab goals. So the lab goals are to find model parameters of an induction motor. We're going to use those model parameters to derive a model and use them to interpolate along your collected data from simulations, of course. And we're going to also answer questions about induction motors. Those are the main goals of the lab. So in terms of lab submission, as usual, you just need to submit the answer spreadsheet. Everything is contained in your lab package. And now we're going to go over tips. We're going to go over PSIM tips, how to use it, and what is the relationship with the spreadsheet. Instead of just going over PSIM and then over the spreadsheet, I'm just going to cover both at the same time. And we're going to also take a look to the textbook, section 611, and some others, but this is the main section from which this lab stems. And it's pretty much everything you need for the lab. So let's now go with PSIM. I'm going to walk you through the different tests. So the first test we're going to run for this lab is the DC test. And so basically what we need to find here is the internal resistance of the motor. And what we're going to do is use this circuit here, for which you need to change the supply voltage. So let me go to the template to walk you through that. So for the DC test, use DC test. And what we need to do is to make sure that we change the supply voltage. So we need to change this supply voltage here until we read in IDC the value that we have as the nominal value assigned to your group number. So, but you need to take two measurements. You need to take the IDC, which should match this one, and then you need to take the DC voltage for which this current occurs in the motor. And so basically you change this, you simulate, and you put the IDC and the VDC, bringing it here. So I already selected those, and as usual you measure. So as you can see, it goes pretty much to steady state quite fast, and there's a reason for that. And so once you see the 3.26 volts sort of that you have attached to your group, which voltage this occurs for, and you put those values in here, and from that you need to compute the RDC for this machine configuration. Okay, and so you need to also put in here the formula that you need for that. Okay, the book covers this particularly well. So in section 611, you're going to have this subsection, the DC test for stator resistance. And so this is the same configuration that we have in PSIM, and the goal is to measure RD, the DC resistance on the machine. But remember, this is the internal configuration, so your machine is configured as a star circuit, and so you can have two different ways to compute RD, and depending on which one you use in further analysis, you're going to have to use one to make a modification. Okay, so so pretty much you can compute RD as the sum of these two R's, or you can just compute one of them. And depending on what value you get as RD for the template, you then may need to derive the second another variation of that for future analysis. Okay, just keep that in mind, because maybe you use the incorrect value for the per phase circuit, equivalent circuit of the machine, and then your results are going to be off. So it's just probably because of this. Okay, and so I would recommend that you go with the one that is in the book, because that's the one we're going to use. Okay, So now, so once you have RDC, then you need to answer these questions under what assumptions you can do this. This question 2.3 is here, but it's not in your template. And the reason for that is because we simplified the lab. So you don't have this question in particular because you're not taught these things, but they are usually in the program for the course. Then we move to the no-load test. So the no-load test is this circuit here. And so the no-load test is the same, is equivalent to the no-load test in a transformer. So basically what we do in this case is we excite the motor, we let it run, and then we measure different values. What values do we need to take out from this experiment? Well, we need to measure I1, I2, I3. As you can see from my particular case, they are going to be pretty much the same. The frequency is fixed, it's 60 Hertz, but you need to measure P1, P2, take out the power factors, then compute this input power, and this IL is pretty much the average of the different phase currents, and you need to compute the phase voltage. The phase voltage is computed here the same as you will do for a three-phase circuit. So you cover that in lab 1. So this is going to be familiar to you. Now, how to take these different measures here. So basically, you don't have to do anything to the machine. You just need to let it run and then just go and read the different values that is given to you. So for that, we're going to just run this no load test. And now we need to choose what kind of measurements we want to make. So one of the most important measurements you're going to take from here is the powers. So P1 and P2. And if you come to the book and we check out the circuit for that particular experiment, this is the configuration that we have in the machine, and it's the same that we have in the PSIM circuit. So we need to take P1 and P2. In here, they're put in two watt meters to do those measurements. But in PSIM, we just need to put the ammeters and voltmeters and let PSIM make the calculations for us. So what you need to do is you need to put in one plot, in one figure, one voltage and one current. And in the other one, in another window, you're going to have to plot the other voltage and another current. Which ones are those? Let's go back to the circuit and I'm going to show you. So for P1, you need I1 and E1. And for P2, you need I2 and E2. So we need to choose E1 and I1. And that's going to be our first window. Then we split the window, adding one screen. And we put E2 and I2. And now we have the two values that we need. Remember, and now I just bring in the cursors and I just for sure get the machine in its steady state configuration. And what we need to do is to measure what are going to be the RMS values for the for E1. And as you can see, I1, I2, and you can be certain of that I3 is going to be the same because it's a simulation. But if you were in a real environment, you would have to measure the three of them, okay? Because there are small variations in the in the machine, so resistance are not exactly the same, and there are other factors that are non-linear that are going to be present. How the screw cage is made, or it has imperfections, and that can change a little bit what the current is going to be on each of the three phases. But because this is a simulation, you don't have that issue, okay? So, and now, as you can see, we have an RMS value of 208 volts, which is exactly the supply voltage. in RMS value. But now you need to take here the measurement of the three currents and the two powers. So as you can see, P1 is going to be positive, 244 watts in this case, and minus 144 watts is going to be P2. So that's pretty much what I have here. And you can also get the power factors directly from PSIM. So the PSIM power factors are here, and so you get those power factors. If you don't see them, right? If you don't see the power factor, it's because these buttons here might be off. So if you want to see the power factor, you just click here on the power factor bar, on this toolbar, on the power factor button, and you're gonna get the power factor. And so you collect the two powers, the two power factors, and you put these values here. This is the average of the three currents, and this is the phase voltage that you will compute, as I said, the same as with the three-phase circuit that we covered in Lab 1. And now you need to answer why P2 is negative, because this is quite interesting. Well, why this value is negative is very important. As you can see, the first time you measure this value, you see that P1 is 244 watts, but the input power is 98.8 watts. Okay, and this is interesting because we don't have a way to measure Pn, but you can get Pn from P1 and P2. This is all the power that is delivered to the machine, and this is one positive, one negative, and that negative one is very interesting. And then you need to answer these questions, and then we move to the blocked rotor test. So for the blocked rotor test, we're going to use, let me close this one. We're going to use this circuit here. And as you can see, it's pretty much the same as the no-load test. So you have the same machine configuration, right? The difference is that in this one, we let it spin freely. But now for the block rotor test, we're putting here a load. And if I double click on this load, this is a mechanical load of constant speed. And because I'm putting the speed to be 0, this is basically blocking this machine rotors from moving. So anything that we measure here is the equivalent of having the machine blocked. In a real lab, you would have to put something that doesn't let the rotor move. But well, here in the simulation, what we use is a load of constant speed. Now, this circuit configuration is the equivalent to a short circuit test for a transformer. So this is very similar to a transformer's short circuit test, and that is the relation, the link that there is between induction motors and transformers. Okay, so what we need to measure here? Let's go take a look to the template. For the block rotor test, we are going to rise the supply voltage from 0, okay, until you reach the nominal value specified below. This is interesting because remember that when we talked about transformers, the short circuit test, you have to go from 0 voltage very slowly until you reach the nominal current in the secondary. If you go too fast, you can damage or burn or destroy the transformer. The same applies to the motor. You can't just put here in the supply voltage the nominal value, because if you do that, you will just basically burn the motor. Or if the motor has some electrical protection, you're just going to trip those. But that's not what we want. So you have to move from 0 going up in the supply voltage until you read the nominal current flowing through I1 or any of the other phase currents. So the I num the nominal current in this case is 3.26 amps, and so you need to raise E1 until you get that value of 3 or close to 3.26 amps. And now what is interesting here is that the frequency that this is very important. It's very important that you know the frequency, because we're going to run this test at 25 hertz instead of 60. And when you go and you read on the book why this is done this way, you will understand why. And now this is to compensate for the fact that some circuit parameters are going to change in the machine if you were to use 60 hertz. So to compensate for that, because this is not a transformer, it's a motor, it's a different machine. You choose this frequency depending on the class of the motor. We're using a class A. So just go read the book. It's very clear on why we do this. But you need to know that this test is run at 25 hertz because you're going to use that frequency in future calculations down the road. So now, what we need to do here is to, of course, these don't really match because I think I've changed the lab number, the group number, but you need to reach this specified current in your phases. Okay, and now what you do is you do pretty much the same. You simulate this circuit until you get this reading here, and after you arrive to that condition, let's assume we are at that point, what you need to do is to collect the data. Same window configuration, so we need to plot E1 and I1, and now I'm going to bring this in. You need to split this window and add another one. Now I2 and E2. And as you can see here, the machine is not moving. That's why it's pretty much on steady state since the beginning. And what we need to do here is to, again, collect the nominal values that we need to have. So in this case, for this circuit state here is 25 volts and 3.05 amps. And now we have two powers. We have 75 and 65. Okay, and the two power factors, and that is what you need to note in here. So I have 75.8, 65.8 watts, and the two power factors, and the PN is 141 in my case. The same approach, the average of the currents, and the phase voltage is the same as you computed for a three-phase circuit. And so once you have done that, you need to choose what is the right choice for the given assumptions under which we can run this test, and what could be the estimation of motor slip under the blow rod condition. And there is something interesting. If you look at question 3.2 and 3.3 and you compare them to 4.1 and 4.2 respectively, you may think this is the same question. Well, it's pretty much the same, but the answers are going to be completely different because the assumptions and the conditions for the slip are different for both tests. And that's what we want you to show us, that you know what assumption you can make when you run the no load test, and what is the estimated slip for that condition, and what is the assumption for the block rotor test, and what is going to be the slip at that condition. And then after we're done with that, we have pretty much all that we need to compute the different equation, the parameters for the model. So here we have R1, and remember, you have RDC from there, depending on what value, what equation you use for RDC. Then you need to probably go a step further to compute R1, or maybe not. And so for the no load test, you're going to do all these calculations. and they may look like pretty daunting, but you don't have to worry too much about it. Why? Because the book covers all of that in thorough detail. So basically what's going on is that this section 6.1, will walk you through the process of computing all those values. Okay, everything is explained here. They're giving you the equivalent circuits, how they work, what simplifications you can make, and all that is explained in this section. And then they go and cover the DC test and all the details with this one, and the locked rotor test with more. So you see it's the same circuit as the previous one. The difference is that now we block the rotor, and in this case this is the equivalent circuit, and it goes and shows you all these impedances and different power factor involvement and all that stuff. Is the good stuff that you need to know to go and complete the lab. So to read here, it's very clear. It doesn't make much. It doesn't make much sense for me to read this for you. You can do it yourself, and you're gonna have to work with it. And now, then, the most important thing. So that's all the explanation. That's all good, because you're going to understand why you're doing the things that you have to do. But then you have this example here, example 6.8. And example 6.8 is giving you a set of measurements for a motor, right? And with these measurements, then they go about and compute the machine parameters for all the tests, okay? And they give you the different results, all the equations with all the solving part for those equations that you need to get in order to compute the machine parameters. Okay, and so this is going to be very, very important for you to follow up. Of course, you may have to go back to some other sections in this chapter to understand some intermediate values that you have to compute here, but this is pretty much all you need to know. For example, remember when I spoke about the frequency of the locked rotor test? They are using here 15 Hertz. I'm using 25 for our configuration, and there's a reason for which you have to choose one of these or the other, or 15 or 60 Hertz or some other different frequency. Okay, but it's explained here. But this is a very important point, because we usually assume that our frequency is 60 Hertz for everything that we do, but it's not the case in the locked rotor test for the induction motor. You will run that usually at a different frequency to compensate when you compute and estimate the parameters. So as you can see here, for estimation of parameters, we have parameters that are derived for each particular test. So we have R1 for the DC test, we have this impedance for the no-load test, right? So it's a no-load test impedance, and we need to find this power and the power in the rotor, and then we move to the other test, and we need to compute this. Then we sum up. So pretty much the few last parameters are a combination. Is a parameter that involves not only values from the locked rotor test, but also from the DC and the no-load test. And those are the most important values that you need to compute. Why? Well, because then comes the next section. So section 6 requires you to go and use the induction motor torque speed experiment. And let me show you this one. So for the speed torque speed characteristic, now we have two different sensors. So you see here, it's pretty much the same. You don't have to change anything in the motor. It's the same speed meter, and now we have a torque meter, and we have here a load. Okay, and so what's going to happen here is that you are going to change the speed of the load. So we're going to go from 0, which is block rotor, to 1800, which is the synchronous speed, which is the maximum that you can get. Okay, and so what is going to happen is you're going to measure the torque. So basically what you're doing here is you are using this speed load, right, as the independent variable, and then you are going to measure and take the measurement of the torque in the machine. Okay, and now you fill up these values, and you should get this curve, which is quite cool. This is a very interesting curve, and that is going to come from these values that you're going to measure. Okay, now what we need to do for this particular test is we're going to use these parameters here, right? And we're going to go a further step, right? And find the Thevenin voltage, the Thevenin resistance, and this Thevenin reactance. And from those values, we're going to compute these values here. Is the slip, the current, the air gap power, and induced torque. And if you do that well, you're going to end up with this. This is the model. This is the computations that you're going to obtain from running these values here. So remember, here we have the induced torque, and here we have the speed in RPMs. So what is going to happen is that you need to do all these intermediate calculations so you can get the induced torque, okay, with the equations from the book. And for this one, you have to refer to previous sections, okay? And so what you're going to have to do is to review all the material that you know from your lectures, so that you can compute the slip, the current, the air gap power, and from that the induced torque. And when you have that and you compute those for your values, this is what you're going to end up with. You're going to be able to interpolate this model over this curve. And that is exactly what we want. We want you to be able to compute these motor parameters, so you can pretty much compute any point in this curve that you want. And that's exactly the goal of these tests. If you have a motor and you don't know its parameters, you run these 3 tests: the DC test, the no load, and the block rotor test. And from those, you compute the equivalent circuit parameters. And from the equivalent circuit parameters, you can then run the simulation and find the Thevenin voltage, the Thevenin resistance, and so on. And then you're going to be able to compute any point in the curve that you want. So, and a question that most people are usually interested in are, what would be the torque that the machine can produce if I put a load that is running, is spinning at 1200 RPMs, right? So we have this measure value here, right? But remember something. If you have the machine parameters, you don't have to do this. You don't have to do all these measurements, right? If you have the machine parameters, you can just come directly to this point here and estimate the induced torque equation from these parameters. And you can pretty much know, just by evaluating the induced torque, given some input speed, what is going to be the induced torque for that machine. And that is pretty cool. And the reason why it's so cool is because it's really easy. It's really easy to run the DC test, the block load test, and the no load test compared to trying to do this characteristic curve. And why so? Well, it's very difficult to find a load you can spin very, very well at a precise speeds, and that can go all over this range from zero, like blocking the motor, until the maximum. Imagine you have a big motor, big motors, running a blocked rotor test on them with a dynamic load is not easy at all. So you can pretty much block the rotor if you really want to, and that can be very, very expensive because you're gonna need a huge mass so the motor doesn't move to run this test. But if you have a machine that you need to connect to this rotor, so that load changes at your because you control it, it's very difficult. In simulation is super easy. I just need to change a number, but in real life with big machines, this can be very well impractical. And because it's impractical, it's better to just run the 3 previous tests, compute the parameters, and then you have this. But the goal of this analysis is to show you that you can have a characteristic curve, which is the measured, we constructed, but you can estimate very, very well if your parameters are well computed over that curve and have a pretty good idea where you are. And that's the idea behind this section here. And now for section 6.2, you're going to compute the pull-out torque and specify the equations that you need for that. Okay, so I'm giving you a hint. Okay, if you do the computations up above well, you get this bonus result, right? I'm giving you the T max, the maximum torque on the machine, and of course your pull-out torque has to be very well the same. Okay, so if you do everything well, you're gonna get exactly the same results. So let me go in the book and try to find for you what other sections you need to take a look at that are important. So yeah, I would recommend that you go over the equivalent circuit section, which is section. So you need to definitely read. So starting from chapter 6, just take a look and read here. What is the construction of the machine? That is interesting and all that. But so the development of induced torque is very important because you remember are going to compute that value in induced torque. You also need to read carefully section 6.3, the equivalent circuit of an induction motor. They walk you through the different calculations, the rotor circuit model, and all that. There are valuable equations here that you need to take into account when you work on section 6 of the template. Okay, and so you're gonna find the equations that you need. Okay, and here's the torque speed characteristic equation. These are the equivalent circuits. Okay, and here is a VT, Thevenin voltage you need to compute. That's why we need all those impedances from previous section, when we run the tests. And this is the induced torque, and all that is pretty much on page 334 to 336 or something like that. Okay, and so that's all you need to complete the lab. Thank you very much for your time, and I hope you have a great lab.